Our final derivation is for something called a toroid, which is basically a solenoid that has been twisted around until it closes on itself and it becomes a circular shape, rather like a donut shape. So the way we're going to approach it, you can see this shows it from the side in a cross section, so that you've got the wires around the outside that you can see the cross section of have current coming towards us, and the wires on the inside have current going away from us. Now we're interested in finding the size of the magnetic field at a distance r from the center. So we'll show later that there's not much point trying to work it out for outside the whole toroid, but for down the middle of the donut, in between the inner and the outer bits of wire, then you have the magnetic field is running in a circular shape, and in the same circle shape, parallel to the magnetic field lines, we have our loop that is going to be a circle with a radius r. So again, this shows a cross-section of our toroid, and what we have is wires you can see coming towards you along the outside of the toroid, and then you can see the wires on the inside with current going away from you. So the magnetic field will be going in a circle around the loop, just like in a solenoid. Remember, the magnetic field runs down through the coil. Here the coil has been turned into a circle, so the magnetic field goes in a circle, and we take our Amperian loop in that same direction as the field, so around the circle. And so all the points on the loop are a distance r away from the center. So we have our equation that B times ds is mu naught times the enclosed current. So B, since it's a constant around there, times ds around a circle, which is 2 pi r, equals mu naught times the current in one wire times n, where n is the total number of turns. So we have B equals mu naught I over 2 pi r times n. So that's for the magnitude, the direction you get from the right-hand rule. Now we can actually prove that if we took a loop outside, that the magnetic field outside would be 0, because for every bit of current coming out of the screen around here, the same amount of current is going into the screen here. So for any loop outside the toroid, the net current inside is 0, and so there'll be no magnetic field once you are outside the currents along the outside of the toroid.